Every time you ask ChatGPT a question, every time an AI creates an image, every time a self-driving car learns, there is a very good chance one company is making it possible: NVIDIA. But how did a gaming company become the most important company in artificial intelligence? On April 5, 1993, three engineers met in a Silicon Valley diner with $40,000. Jensen Huang of LSY Logic, alongside Sun Microsystems veterans Chris Malachowski and Curtis Preem, wanted to accelerate three-dimensional PC graphics. They entered a crowded market dominated by 3DFX and ATI. NVIDIA's first chip, the 1995 NV1, failed because it ignored Microsoft's emerging DirectX standards. A failed Sega console contract soon pushed the company to the edge. With 30 days of cash left, Huang persuaded Sega's president to convert their final contract payment into equity, a critical $5 million lifeline. In 1997, the DirectX-compatible Riva 128 saved them, selling millions. 2 years later, the GeForce 256 offloaded geometry calculations from the CPU. NVIDIA called it a GPU. It was designed for video games, but its underlying mathematics would soon calculate something far more powerful. To understand why, we have to look inside the silicon. A standard CPU is like a team of 4 brilliant scholars. They can solve incredibly complex, diverse tasks, but they must do them one at a time. A GPU, by contrast, is like an army of thousands of elementary school students. They can only do basic arithmetic, but they can all calculate at the exact same moment. For video games, these thousands of tiny cores calculate the color and position of individual pixels simultaneously. But this exact mathematical structure, massive grids of simple additions and multiplications, perfectly matches the math of deep learning. Neural networks do not need complex decision-making. They need millions of matrix multiplications over and over again. By the early 2000s, NVIDIA introduced programmable shaders, allowing developers to write custom instructions for these cores instead of relying on a rigid preset pipeline. But a massive bottleneck remained. Huge pools of mathematical weights and activations had to move instantly, making high memory bandwidth just as critical as raw processing speed. Then, in 2006, NVIDIA made a high-stakes gamble. They announced CUDA, a software platform and programming model that allowed developers to write standard C code to run directly on the GPU. The 2007 toolkit gave researchers compiler tools, a runtime environment, and libraries, bypassing graphics code completely. This was a massive financial risk. NVIDIA spent hundreds of millions of dollars putting CUDA capability into every single chip they sold, driving up manufacturing costs for a market that did not yet exist. The company was asking serious scientists, physicists, and engineers to build their entire software future around hardware designed to play video games. If the gamble failed, NVIDIA would destroy its own margins. If it succeeded, they would own the foundation of a brand new computing era. For decades, artificial intelligence was stuck in a theoretical loop. The math for deep learning existed, but researchers lacked the data and the raw power to make neural networks actually work. That changed in 2012. Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton entered the ImageNet visual recognition competition. They built a neural network called AlexNet, but instead of using standard computer processors, they wrote custom code to run on 2 consumer-grade NVIDIA GTX 580 graphics cards using CUDA. The results shocked the computer science world. While traditional systems took weeks to train, the GPUs finished the job in 6 days. AlexNet blew past the competition with an unprecedented 15.3% error rate, a massive 10-point lead over the runner-up. This was the spark. It proved that deep learning was no longer a theoretical science, it just required massive parallel computing. Almost overnight, researchers abandoned traditional processors and made NVIDIA GPUs the default platform for AI development. The breakthrough quickly spread from recognizing images to predicting proteins, generating art, and training massive language models. Suddenly, a new multi-billion-dollar race was born. Giants like Google DeepMind, Microsoft, Meta, OpenAI, Anthropic, and xAI realized a fundamental truth. In the new era of intelligence, the company with the most computing power wins. Every scientific breakthrough would now require an even larger mountain of silicon. The race was no longer about software, it was about physical infrastructure. To feed this hunger, NVIDIA had to evolve. They moved past consumer graphics to build the Tesla line, a dedicated path for server-grade acceleration. Then came the DGX systems, which packaged multiple accelerators into ready-made AI supercomputers. These servers were not just isolated graphics cards, they were tightly connected systems of processors, high-bandwidth memory, and advanced networking, all engineered to work as a single brain. In 2022, NVIDIA launched the H100, a chip that quickly became the ultimate status symbol of the generative AI boom. By 2024, they announced Blackwell integrated platforms designed to scale this infrastructure even further, but a massive bottleneck emerged. Building these processors required advanced semiconductor manufacturing and specialized packaging, making NVIDIA completely dependent on foundries like TSMC. When a global chip shortage hit, supply choked. This scarcity transformed the economics of Silicon Valley. A single H100 board easily commanded $30,000, while complete multi-GPU systems sold for hundreds of thousands. Tech giants and cloud providers realized they could not wait. They began committing billions of dollars to build massive data centers, launching an infrastructure scramble to secure enough raw compute to train the next generation of models. With demand far outstripping supply, the bargaining power shifted entirely. NVIDIA was no longer just a component vendor waiting for orders. They had become the central gatekeeper of the global technology economy, deciding which companies and which nations would get the power to build the future. Buying the chip is only the first step. The true barrier for competitors lies in the software ecosystem developers have spent nearly 2 decades adopting. NVIDIA layered proprietary libraries like cuBLAS, CUDA, and TensorRT directly into the foundations of AI, while normalizing their platform in university classrooms and cloud partnerships globally to secure access for every rising engineer. To coordinate massive clusters, teams depend on NCCL, Nsight, and high-speed InfiniBand networking acquired through the 2020 Mellanox merger. This tight integration of NVLink, GPU Direct, and hardware-software alignment creates an immense, defensive trap. Swapping to a rival processor requires rewriting millions of lines of custom code, retraining entire engineering departments, retesting models, and rebuilding physical data infrastructure from scratch. The silicon itself is easily replaceable. The relationship between the chip and the code is not. Silicon Valley's rivals are fighting back. AMD's Instinct MI300X packs massive memory bandwidth, using ROCm software to run heavy language models. Intel's Gaudi 3 targets cost-sensitive enterprises, while hyperscalers design custom silicon. Google's TPU, Amazon's Trainium, and Microsoft's Maya chips let platforms bypass external hardware. Even under tight export controls, Chinese firms like Huawei are building domestic Ascend processors to bypass global supply chains. But as data centers hit physical power and cooling limits, raw speed is no longer the only metric. Competitors must still prove their software can match the full experience developers expect. The battle is shifting from remote data centers to the physical world. In warehouses, Jetson modules run edge processing, analyzing data directly on local devices. On the road, the Drive platform manages split-second vehicle decisions, while Omniverse creates digital simulations to test autonomous machines and digital humans before they exist physically. This architecture reaches into clinics for drug discovery and powers GRACE systems for climate modeling. Yet, the ultimate frontier is AGI. If future AI agents require massive scale, hardware demand will explode. If algorithms become hyper-efficient, that demand could evaporate. Whether accelerated computing remains the default way we build intelligent systems is an open question. NVIDIA's ultimate triumph wasn't building faster chips, it was positioning itself as the toll booth for human progress. In the race for AGI, we aren't just buying hardware, we are leasing the future of intelligence from a single company. Share your thoughts on NVIDIA's dominance below.